In this video, we will solve the test case prioritization problem using particle swarm optimization algorithm. So this is the final output. You can see the priority values for test case 1, test case 2, test case 3, and the priority values for test case 4, for test case 5, and in the end you can see the best priority order. So here you can see this is the best priority order. Now we will apply the particle swarm optimization algorithm to solve test case prioritization problem. Particle swarm optimization algorithm is already discussed in previous videos. In this video, we will apply this algorithm to solve test case prioritization problem. First, initialize algorithm parameters like population size. We have 50. Maximum iteration 100. Then we have the PSO parameters. Weight inertia 0.5. Coefficients C1 1. C2 is also 1. Now you can see we have the test cases. For simplicity, we are using this. And next you can see we have the weight vector. And in this weight vector, you can see we have 5 values. Each value represents the weight assigned to specific feature or attribute. For example, 0.3, this value is assigned to the first feature. 0.2, this value is assigned to second feature. 0.1, this is assigned to third feature. And this one for fourth feature. And the last one for the fifth feature. And the sum of all these values is expected equal to 1. Next, we have the number of test cases and dimension. So we have the number of test cases is equal to size. Now, this variable here, test cases, so here you can see we have a variable that is test cases. This variable contains all the values for the test cases. Now we are using here size function. This function returns the dimension of the matrix. It means the number of rows in the position matrix. Next, number of dimension we have equal to number of test cases. Done. Now as you can see we have 50 agents. Now we will initialize their position in the search space, and in PSO we will also initialize their velocity. So now we will initialize their position and velocity. Now we will initialize agents position randomly in the search space. So here we are using a rand function that is used for normally distribution of values within 0 and 1. And here we have number of test cases. This one, dimension and population size. That is right now 50. Done. Now we'll initialize the velocity for each particle, that is initially 0. Population size and number of dimension. Done. So initially we have velocity 0. So for this we are using here zeros function. Now in PSO, as we need agents personal best value and the global best value. So now we will initialize their personal best and global best values. Personal best we are using here PBest, that is initially position. Global best, that is GBest. We have empty that we will update during evaluations. And now we have the global best fitness, that is infinity. This is the positive infinity value. It means initially no fitness value have been evaluated. So now you can see we have population size 50, maximum iteration 100, PSO parameters, test cases, weights assigned to features, and then we initialize the position for the agents randomly. Velocity is 0, PBest, GBest, personal best, global best. Now we will start the PSO main loop. Here, the current iteration we have for current iteration 1 to maximum iteration. Maximum iteration we have 100, so this loop will repeat 100 times, and after that it will display the best test case order. Now we will evaluate the fitness value for the agents in the current population. So here I am using the fitness variable. So here I am using the fitness variable that will hold the agents fitness values. So we will apply the objective function on the current population. This is the objective function name. So here we have different parameters like positions, test cases, and weights. Position, test cases, that is this one, and weight assigned to each feature. Now here you can see the objective function name we have, calculate fitness. Now we will initialize the fitness function. Here we have a function, it's variable fitness, and the function name we have calculate fitness. Then we have input parameters, positions, number of test cases, and weights. Now first we have the population size, then using this size, so we are using here the size function to access the agent's position from the position matrix. Then the number of test cases, using size, test cases, then fitness, that is initially we have 0. Now for each particle 1 to population size, we will check the, now we will calculate the test case order. So here we have the test case order, that is position P. Here we have a new variable, that is test case order. It will determine the solution P from the position matrix. Now we will solve the test cases. Now we will use a new variable, that is record test case, to store the result. Here we have the test cases from the, and we will store by index. Now we will calculate the fitness values based on this new variable. Now here we will calculate the priority store, that is the sum of all the elements in this into weights. So here we have two arguments. First you can see here this one, it represents the element wise multiplication, and here 2 which indicate the dimension for the summation. Fitness for P we have minus sum priority. So here we will sum all the elements in the priority score. So here we have the unary minus, it means higher the fitness value results in lower fitness value. Here we have the test cases. Update the personal best and the global best value. For that we will do for each particle. So first we will update the personal best value for each particle. So we have a new variable that is update PBest, that is equal to, now we will compare the fitness value if it is less than the fitness function value. Now if this condition is true, the PBest updated value we have new updated value for the PBest. That is equal to the position. Now we will update the global best value. Global best we have empty. So for global best value we will rank the solution and then we will consider the minimum among all as the global fitness value. Now we will find out the minimum fitness, and here we have the minimum index, minimum fitness. Here you can see we are using this min function to calculate the minimum fitness value. We will check if this minimum fitness value is less than global best fitness, that is GBest fitness. Then if this condition is true, we will update the GBest position. Then we have the minimum index. We will access the value by the index. Then we will keep the global best fitness, that is the minimum fitness. Then now the global best is updated, personal best is updated. Now you can see here we have the population size 50. For 50 agents, we initialize the position, velocity, calculated the fitness value, updated personal best, global best for each particle. Now as per particle swarm optimization algorithm, we will move the search agents in the search page. So now we will update their position. So for that first we will calculate the velocity so that we can add the velocity in the current position and the position is updated. And then we will display the best solution. Now we will update position and velocity for each particle. Position we have randomly initialized, velocity is 0. Here you can see in the particle swarm optimization algorithm, this mathematical equation is used to calculate velocity and the position. So here velocity is calculated, weight inertia, previous velocity, coefficient R1, that is the random value, agent personal best, and we have the global best, and then we will add this calculated velocity in the current position and then the position is updated. So here we will write the code for this velocity first. Here we have two random number R1 and R2. So first we will take the random number R1 and R2, that is equal to, so here we are using the rand function that is used for normally distribution of the random values within 0 and 1. So we are using here the rand function, population size and the dimension. Same we will do, same for the second variable. Now we will write down this velocity formula here. Here this is the velocity calculation, then final position is updated by adding velocity in the older position. Now all calculation is done. Now we will display the best test case order. So here we are using the display function. that is best test case order. So we will display here the global best fitness. Slight error we have. Now we have the new position, that is in the previous position at some velocity. So slight error we have. Here we have the PBest, that is a personal best, global best, and then population size position. Now we will run the code, and here you can see, the output best test case order, and then you can see here we have the input. So here you can see this is the test case second, so this is 2, next again 2, next 2, and 0.12, that is 4, and then we have 612. So we have the test case order 222, 42. Again we run this code. Next you can see here, first we have 0.6376, that is 5, 5, 1. This is the first test case. Then 3, and here this is 1. So this is the test case order 55131. So here we have 50 agents. We will repeat this loop 100 times. This is the input. Here you can see we have test case variable that contain the input test cases. Here you can see we have the input test cases. Then we have the weights that indicate the weight associated with the features. Now we have the number of test cases, dimension, initialize the position randomly, calculate the velocity, personal best, global best, and then repeat the loop until the stopping condition, that is 100, it is met. And then we have the fitness function we have, and next you can see we have the fitness function, calculate fitness, that is applied here to calculate the best test case order. So you can modify the code and display the test case priority using this, and here you can see the best test case order for this. So that's all about this video. If you have any question, you can comment below, and thanks for watching this video.